In this video, we're going to do some extra examples for determining where a function is increasing or decreasing and finding its critical numbers. So let's get started. So this example 1a, we want all the increasing, decreasing intervals. So our function f of x is a polynomial. So the first thing we want to think about is the domain. Okay, so when you have a polynomial function, the domain is always all real numbers, or from negative infinity to infinity. So there's no places where the function does not exist. Maybe I'll just write that. Okay, so no x where f of x does not exist. So remember, those are one place where you can switch from increasing to decreasing, so we want to find those values as well. Okay, so we don't have any of those, so now we want the critical numbers. So to find the critical numbers, we're going to start by taking the derivative. So for polynomials, that's pretty straightforward. We just need the power rule. So it's going to be 3x squared plus 6x minus 9. And I want to set this to 0, so I'm just going to, I see that I can pull out a 3. Okay, and then I can actually factor this. So I think it's going to be x plus 3 times x minus 1. Okay, so there's my my function, my derivative. So now I want to know, okay, so where is this equal to 0? Okay, so that's when 3 times x plus 3 times x minus 1 equals 0. So this is going to happen when one of these factors is 0. So 3 can never be 0, but I have 3 things multiplied together here. When you have things multiplied equaling 0, it means one of them has to be 0. Okay, this one can't be 0 because it's 3. So it means one of these two factors has to be 0. So that means that x plus 3 is 0 or x minus 1 is 0. So we get x equals negative 3 or x equals positive 1. Okay, so these are critical numbers for our function. Now we also want to check where does the derivative not exist. Okay, but there's none of these since the derivative here is also a polynomial. So polynomials exist everywhere. Okay, so we don't have to worry about that. So our only critical numbers are negative 3 and positive 1. So we want to break our domain into these intervals. So we do our number line. I'm going to have negative 3 on here and positive 1. So those are where the derivative is 0. So these are the only places where we can change from positive to negative or negative to positive. So I want to check a number in each interval. So maybe I check minus 4 because that's less than minus 3. So I'm going to plug that into so I'm just going to write here, this is f prime of x. So plug that into the derivative. I like to use the factored form. So this is going to be 3 times negative 4 plus 3 times negative 4 minus 1. Now you could compute this number. I don't actually care what it is. I only care if it's positive or negative. So I'm just going to note that 3 is positive, negative 4 plus 3 is negative, and negative 4 minus 1 is also negative. So I have a positive times 2 negatives. That's going to give me a positive number. Okay, so that means I'm going to be increasing on this interval. Okay, something between negative 3 and 1, let's pick 0 maybe. So that's 3 times 0 plus 3 times 0 minus 1. Again, you could compute this number, it's just negative 9, but it's sometimes useful to think about it just as positive or negative. This is why I like to use the factored form. Okay, you can't really do this when you have it as addition and subtraction because it matters which part is bigger. So it's going to be a positive times a negative. So here we're going to get a negative, so we're going to be decreasing. Something bigger than 1, let's say 2. So it's 3 times 2 plus 3 times 2 minus 1. Now all 3 of these factors are positive, so I'm going to get a positive, which means I'm going to be increasing on that interval. So I can write my answer now. So we're increasing on the interval from negative infinity to negative 3, and then again on the interval from 1 to infinity. And we're decreasing on the middle interval, negative 3 to 1. Okay, so that would be where the function is, increasing or decreasing. Okay, let's try another one. So here g of x is x plus 1 over x minus 1. So remember, the first thing we want to do is think about the domain. So for this function, we can't have the bottom equaling 0. So I can't have x minus 1 equaling 0. So I can't have x is equal to 1. Okay, so any other x is fine. So I wrote x not equal to 1, or another way to write that is from negative infinity to 1, and then from 1 to infinity. So we're just excluding x equals 1. So we want to remember to include x equals 1 in our number line. I'm going to write in our table. Okay, so now we want to find the critical numbers. So we want to take the derivative. So g prime of x. To do this, I'm going to use the quotient rule. So the derivative of the top is 1 times the bottom, as it is, minus the derivative of the bottom, which is also 1, times the top, as it is, all over the bottom squared. Okay, so then I'm going to have x minus 1 minus x minus 1 over x minus 1 squared. Okay, these x's are going to cancel, and I'm going to get minus 2 over x minus 1 squared. So now I want to find my critical numbers. So where is g prime of x equal to 0? Okay, so that's when this fraction is equal to 0. So you could think about multiplying both sides of this equation by x minus 1 squared. That's going to kill off the bottom. Okay, it's going to say where negative 2 is equal to 0. This obviously never happens. So there's no x's for which the derivative is 0. Now I want to think, okay, where does the derivative not exist? Okay, well that's going to be when the denominator is 0. Okay, so that's going to be when x minus 1 squared is equal to 0, which is when x equals 1. Now, so we get this value. Just want to point out, this is not a critical number. Okay, since it's not in a domain. Okay, but we are still going to use it on our table. So in fact, x equals 1 is the only thing we're going to have on our table here. Okay, so we make a number line, and 1 is the only place where it can switch. Now, the derivative does not exist there. So we try something less than 1, let's say 0. Now you might realize that the derivative here is always going to be negative. So why do I know that? Because I have a negative on the top, and the bottom, because it's squared, is always positive. No matter what x I plug in, this is going to be a positive number. So you could use that to say these are both negative, but let's just see. We'll plug in 0. Negative 2 over 0 minus 1 squared. So that's negative 2 over negative 1 squared. Negative 1 squared is 1, so we get negative 2. So this is negative, which means decreasing. If I plug in 2, I have negative 2 over 2 minus 1 squared. That's also negative 2. So it's negative, so it's decreasing. Now, because at 1, so f of 1 doesn't exist. F prime of 1 also doesn't exist. When we're doing our increasing, decreasing, we definitely don't want to include 1 in those intervals. Okay, so it looks like it's decreasing everywhere, but at 1, there's actually no point. So there's a vertical asymptote. Okay, so when we write our answer, okay, so g of x is decreasing on the interval, so on negative infinity to 1, and then again from 1 to infinity. This is its entire domain, so that means that it's never increasing. Okay, so that would be how we give our, ooh, that doesn't look good. Wow. Oh, maybe I could have just, there we go. I guess I need to be more careful with this box feature. That's a bit better. Okay, let's try another one. So again, we're looking where are these functions increasing or decreasing. So our function is x times e to the 2x. So we first think at our domain. Is there any x's we can't plug in? No. So this is all real number domain. E to something, you can evaluate e to any power. So we want to find our critical numbers. So we want to take the derivative. Now here, we're going to need the product rule. Okay, because I have two things with x's multiplied together. So the derivative of the first one is 1 times e to the 2x plus the derivative of e to the 2x, which is e to the 2x times 2, times our first function x. Now, if I simplify this, I can pull out e to the 2x, and I'm left with 1 plus 2x. Okay, so that's my derivative. So, where is this derivative equal to 0? So that's going to be e to the 2x times 1 plus 2x is equal to 0. Okay, so that means, like I said before, when you have things that are multiplied equaling 0, one of them has to be 0. So this means that e to the 2x is 0, or 1 plus 2x is equal to 0. Now, e to the some power, this is never 0. Okay, that never happens, so there's no solutions of that type. So we just get, on this side, x is going to be negative 1/2. Okay, and then we also want to do, where does the derivative not exist? Okay, but again, there's none of these as well. So our only critical number is x equals negative 1/2. Okay, so that's what we put on our number line. So we have full domain, and it only could change at negative 1/2 when the derivative is 0. So we're going to try values that are bigger than negative 1/2 and less than negative 1/2. So maybe let's start on the left side, maybe negative 1. So f prime of negative 1 is going to be e to the negative 2, 1 plus negative 2. So 2 times negative 1. E to the negative 2, e to any power, this is a positive number. Okay, now 1 minus 2, this is a negative number. So a positive times a negative, this is a negative. So we're going to be decreasing on that interval. Now something bigger than 0, or bigger than negative 1/2, sorry, is 0. So if I plug that into the derivative, I get e to the 0 times 1 plus 0. So e to the, you could actually compute this, it's just 1. E to the 0 is 1, and then times 1 is also 1. But you could say, okay, e to the 0 is positive, this factor is also positive, so I'm going to have a positive number. I'm going to be increasing. Okay, so here f of x is increasing on the interval from negative 1/2 to infinity, and decreasing on the interval from negative infinity to negative 1/2. Okay, couple more. Now this one might be a bit scary because there's a ln involved. So we want to think about the domain first. So we know that, maybe I'll do this in different color. So we know that ln of x needs x bigger than 0. Okay, so what we want to think of is this middle part ever less than 0 or equal to 0? And it turns out that it's not. Okay, so 5x squared is always positive, which means, or always non-negative, I should say, so it could be 0. but then I add 4 to it. So this is always going to be at least 4. And down here, again, x squared is always positive. So x squared plus 1 is always at least 1. Okay, so 5x squared plus 4 is always bigger than 0, as is x squared plus 1. Okay, so this is never going to be 0. So here we actually have full domain. And we can simplify it using the log rules to make our derivative easier. This is going to be ln of 5x squared plus 4 minus ln of x squared minus 1 plus 1. Okay, so we have our domain. Now we want our derivative so we can find our critical numbers. So again, I'm going to use this form because it's a bit easier. So the derivative of ln 5x squared plus 4 is going to be 1 over 5x squared plus 4 times the derivative of the inside, which is going to be 10x. And then I want to subtract 1 over x squared plus 1 times the derivative of that, which is 2x. Okay, now making a common denominator, I'm going to have 10x times x squared plus 1 minus 2x times 5x squared plus 4. And now my denominator is going to be these two things multiplied together. Okay, so when I simplify, I want to expand these things in. Okay, so I'm going to have 10x cubed plus 10x minus 10x cubed minus 8x over this 5x squared plus 4 times x squared plus 1. Okay, the 10x cubed and the minus 10x cubed goes away. The other things are like terms. So what I end up getting is just 2x over 5x squared plus 4 times x squared plus 1. Okay, so now I want to think, okay, where is the derivative 0? Okay, that's going to be when the top is 0. So that's when 2x is 0, which means that x is going to be 0. Okay, so that's a critical number. Where does g prime of x not exist? Okay, well that's when the denominator is equal to 0. So I have these things multiplied together. So that means one of them has to be 0. So 5x squared plus 4 is 0, or x squared plus 1 is 0. Now you might already know, or you should already know because we talked about it, these things are both bigger than 0, so they're never equal to 0. But if you want to see explicitly that, if I solve for x squared, I'm going to have x squared is negative 4/5, or x squared is negative 1. Okay, these can never happen. Because when you have a square, you always have a positive number. Okay, so we get no x values where the derivative doesn't exist. So when we do our table, okay, we only have to split at 0. Okay, so let's say I check negative 1. Okay, that's going to be negative 2 over, and then the bottom actually is, like we said, always positive, because this is always positive, as is this. So it only matters what the top is doing. So this is a negative over a positive. This is going to be a negative. So we're going to be decreasing. And when we're bigger than 0, I'm going to have positive 2 on the top over two positive numbers multiplied together. This is going to be a positive, so I'm going to be increasing there. So we're increasing on the interval from 0 to infinity and decreasing on the interval from negative infinity to 0. Okay, one more. I just want to fix that 0, I think. Okay, so one more. So here we want the critical numbers and where it's increasing or decreasing. So here, we want to think of the domain first. So for the domain, we need the bottom not to be 0. and it has a square root, so we also can't plug in a negative value in the square root. So we need x minus 1 to be strictly bigger than 0, which means that x needs to be strictly bigger than 1. So in interval notation, our domain is from 1 to infinity, but not including 1. Okay, so that's our domain. Now we want to take the derivative. So I'm going to use the quotient rule. So it's the derivative of the top. That's going to be 2 times x plus 3 to the power 1 times 1, so the derivative of the inside. Okay, times the bottom. I'm going to write it as to the power 1/2 instead of the square root. Okay, minus the derivative of the bottom, which is going to be 1/2 x minus 1 to the negative 1/2 times the derivative of the inside, which is 1. And then I'm going to have x plus 3 all squared. And then divided by the bottom, which is the square root, or x minus 1 to the 1/2, and that all squared. Okay, so I see some common factors here. Okay, so I have x plus 3 in both of these terms, and I also have x minus 1 to some power in both of these terms. So what you can do is you can take out each thing to the smaller power. Okay, so I'm going to pull out x plus 3, the smaller power here is 1, and I'm going to pull out x minus 1, the smaller power is negative 1/2. Okay, so what's left in the first term? Well, I have a 2, and I had more x minus 1s. I had 1/2 of them, and I took out negative 1/2 of them. So what I'm going to have is x minus 1 to the 1. Because when I expand this back through, I'm going to add these exponents. So negative 1/2 plus 1 is going to be positive 1/2. Okay, so that's how I know that this exponent should be 1. Okay, now when I do the next term, I'm going to have a negative 1/2 and one more x plus 3. And the denominator is just going to be x minus 1, because it's to the 1/2 times 2. Okay, so because this is now factored out and it's to a negative power, now I can drop it to the bottom. Okay, so this is going to be x plus 3, and now I'm going to have x minus 1 to the power 3/2, the bottom, because I had a power 1 and now I need to add a positive 1/2 to it. Okay, now in this bracket, I'm going to simplify. So it's going to be 2x minus 2 minus 1/2 x minus 3/2. There. Okay, so if I simplify this, I get x plus 3 times 2x minus 1/2 x is 3/2x, and negative 2 minus 3/2 is negative 7/2. Okay, now you could leave it like this. If you don't like those fractions there, you could just multiply by 2/2. You don't have to put the 2 into both of these things. Okay, if you multiply, you only need to put it into 1. So if you do that, you're actually going to get x plus 3 times 3x minus 7 over 2x minus 1 to the 3/2. But like I said, leaving here is fine. Okay, you can still find all the things you need to find. Okay, so now I want to know, where is this derivative 0? So f prime of x equals 0. That's when the top is 0. Okay, so I'm going to use the more simplified version, but you can use the original one if you want. So this is when x plus 3 or times 3x minus 7 is equal to 0. Okay, so that means that one of these has to be 0. So x plus 3 is 0, or 3x minus 7 is 0. So we're going to get x equals negative 3, or x equals 7/3, which is approximately, I'm going to write this down, 2.33. Now, Are both of these critical numbers, is the question. So now we want to think, what was our domain? And remember, the domain was from 1 to infinity. So, in fact, x equals -3, this is not in the domain. So we can get rid of it, and we have this critical number here. Okay, now we also want to say, okay, where does the derivative not exist? Okay, that's when the denominator is 0, which means that x minus 1 to the 3/2 is 0, or x minus 1 is 0. So this is going to give us x equals 1. Now this is also not in the domain, because the domain was x bigger than 1. So in fact, our only critical number is 7/3. So we make our number line. Remember that the smallest we can go is 1, so that's where it starts. And then we can split at 7/3. So when you're picking a number, you want to be careful that you don't pick something less than 1 or equal to 1. Okay, so like I said, this is 2.33, so maybe we pick 2. Okay, so f prime of 2, now I want my derivative. Okay, so it's going to be, so I'm using this thing here. Okay, so it's 2 plus 3, and then it's going to be 6 minus 7 over 2, 1 to the 3/2. Okay, so this is going to be a positive times a negative over a positive times a positive. Okay, so the top's going to be negative, the bottom's going to be positive. This is going to be a negative number, so we're going to be decreasing. If I pick something bigger than 7/3, okay, maybe I pick 3, and then I plug that in, it's going to be 3 plus 3, and then it's going to be 9 minus 7, 2 over, and then it's going to be 2 to the 2/3. 3/2. Okay, so then this is a positive times a positive over a positive times a positive. So everything's positive. I'm going to be increasing there. So we're going to get decreasing on the interval. So now 1 is the smallest it can be, and it goes up to 7/3. And then increasing on the interval from 7/3 to infinity. Okay, so you want to be careful that you remember to throw away all your critical numbers that are not in your domain, because the number line that we use is only to split up the domain, so it has to be only the domain.